Oh, hey, didn't see you there. I hear you want to learn more about stars. Well, you've come to the right place. I'm Veal deGrasse Tyson.
And I'm Peel deGrasse Tyson.
And today, we're going to take you on a stellar journey covering the temperature of stars, what they're made of, and their distance from Earth.
We know the sun is hot, really hot. But how do we know this? Well, each star has a peak wavelength at which it emits light.
Interesting, Peel. But what is a peak wavelength of light?
Well, every star emits light, right? This light can be placed on a spectrum known as the electromagnetic spectrum. Ultraviolet waves, radio waves, and even microwaves that we heat our food with are placed on this spectrum. While stars can be seen in all the wavelengths on the spectrum, our sun's light is within the visible light portion. If our sun's light is most visible in the green portion of the visible spectrum, we can see that our sun's peak wavelength will be about 500 nanometers. This equation right here is known as Wien's law. This is our star's peak wavelength at which it emits light, and it is equal to Wien's constant, which is this big number, over the temperature of the star in Kelvin. We want to solve for temperature, right? So rearranging this equation, we can see that the temperature is equal to Wien's constant over the peak wavelength of light. Now, we know that our sun's peak wavelength at which it emits light is 500 nanometers. If I do this quickly in my head, 6,000 degrees Kelvin is the temperature of our sun.
Wow, Peel, our sun is piping hot.
Not as hot as you, Veal. For real though, 6,000 degrees? I could toast a million marshmallows on that fire.
Actually, Peel, neither me nor the sun is made of fire.
What?
It's actually made of a soup of protons and electrons called plasma, with a core of atoms being fused together.
Okay, atoms and plasma. Light work, as the kids say.
Actually, Peel, the sun is made up of many different elements, the most abundant being hydrogen and helium, since the fusion of hydrogen into helium is the source of most of the sun's energy. There are also trace amounts of carbon, nitrogen, oxygen, neon, magnesium, iron, silicon, and sulfur.
Holy Copernicus, Veal. How do you possibly know all this?
Well, Peel, remember our electromagnetic spectrum? Well, there's actually another way we can use this to learn about space. When a solid, liquid, or dense gas is excited, or in other words, it's been given energy to emit light, it emits a full continuous spectrum. This can be applied to a star such as the sun, and any other star we can see. Now, when a continuous spectrum of light passes through a low-density gas, such as the sun's atmosphere, the elements in the atmosphere will absorb specific wavelengths of the light, creating an absorption spectrum. The dark lines on the spectrum are where the specific wavelengths of light were absorbed, and when we compare them to known absorption spectra for each element, we can determine which elements were actually present in the sun's atmosphere. We can see that the sun has both hydrogen and helium, since the absorption lines on the star's absorption spectra correspond to that of hydrogen and helium.
Whoa, Veal. You could call me the sun's atmosphere the way I'm absorbing this information.
Wow, Peel, I feel like we know everything about stars. Why don't we go visit one? How about the North Star?
Veal, that's like 400 light years away.
Oh man, you went without me?
Come on, man. I'd never visit space without you. I just used a parallax to figure out how far away the North Star is.
Parallax? That sounds like those pills my grandpa takes with the rhino on them.
Actually, Veal, a parallax is an angle that we can measure to figure out how far away a star is. You can actually observe parallax yourself. Hold your thumb out in front of your face and close one eye. Then switch eyes and you'll see that your thumb appears to move position. If you draw a line from your eye to your thumb, from each of your eyes, the angle between these two lines is what we call the parallax. Let's measure the observed position of the North Star from the Earth. We're gonna wait 6 months until the Earth has orbited halfway around the sun.
6 months later.
Once the Earth has orbited halfway around the sun, we can take the newly observed position of the North Star and see the angle that these two lines form. Half of this angle is what we call the parallax. Looking at this, I can say it's about 0.00750 arc seconds. Using our distance equation, we can see that 1 divided by our parallax will tell us how far away our star is from the Earth. We know that our parallax was 0.00750 arc seconds.
Peel, how many arc seconds will it take for you to stop yapping?
Actually, Veal, an arc second is a measurement of an angle, not a measurement of time. An arc second is actually equal to a 60th of a 60th of a degree. Incredibly small. Now, using our equation, we can now find the distance. 1 divided by 0.00750 is about 133 parsecs. Now, a parsec is equal to 3.26 light years. Multiplying this by 3.26, we can see that our North Star is 433 light years away. Unfortunately, this equation only works for closer stars. If only there is a way to measure those stars that are really far away.
Well, Peel, it's actually your lucky day. The other way that we can determine the brightness of stars, which works for more distant stars, is by looking at the absolute and apparent magnitude of their brightness. The absolute value for the magnitude of the brightness of a star is the magnitude of the brightness at the location of the star, while the apparent brightness of the star is the magnitude of the brightness as observed from Earth, which will be much lower. This is because the intensity of light decreases with distance according to the inverse square law. There's a handy equation we can use with these values to find the distance of a star, where MAP is the apparent magnitude of the brightness and MABS is the absolute value of the magnitude of the brightness. If we use this equation to find the star, say Deneb, whose apparent magnitude is 1.25 and whose absolute magnitude is negative 8.38, we can calculate that the distance from Deneb to Earth is approximately 800 parsecs.
Wow, Veal, now we know everything about stars.
Not everything, Peel. You didn't know that you were my shining star.
We'll see you next time, star fans. Keep on shining.